Okay, class, welcome to it. So we're going to talk about Lesson 5, Exergy in a control volume today. This is the first video of 3 to go over Exergy in a control volume, or oftentimes described as an open system, things like a turbine or a compressor, pump, heat exchangers, etc. We'll dive into that here in just a moment. So as a reminder of what we talked about last class, Lesson 4, Introduction to Exergy. A few items that I want to point out. Exergy is a property, okay? Similar to, say, temperature or pressure. We can use exergy basically to help us define a state. Exergy is not conserved. So unlike energy, exergy is not conserved. It does, however, give us a perspective of usable energy, or is what basically what we can really harness in an engine in a realistic environment. And so it has relationships to energy, but it is not conserved like energy. It is defined with respect to the system's surroundings. So in that case, say you have a very low temperature outside or a very low pressure outside, you're actually going to be able to harness more or have more available work or more available energy to do work. And that's what we describe as exergy. So an engine operating in a cold environment will actually be more capable of producing work than, say, the same engine operating in a hot environment. This is a very important thing to realize. So the performance of realistic engines, performance of realistic systems depend upon the system's surroundings. So exergy, as I noted earlier, represents the usable portion of total energy. So energy is a useful concept, and it kind of gets used in the general public, energy that is. But for engineers, particularly for thermodynamicists, exergy is actually the much more critical idea. So two different bodies could actually have the same amount of energy, but distinctly different amounts of exergy. And that exergy is the usable portion of that total energy. Exergy is destroyed in all actual processes. So this goes back to that exergy not being conserved. It is destroyed. And this is an alternate expression of the second law of thermodynamics, right? So second law of thermodynamics telling us that basically we cannot have perpetual motion machines and that we have entropy production. So entropy production is analogous to exergy destruction. So it's destroyed in all actual processes. We have exergy that is destroyed. Along the lines of actually figuring out exergy analyses, we will often focus, or not just focus, we will often need to do entropy change, or at least to calculate the magnitude of entropy change. And so for steam and water, we're going to end up using tables. That's actually more related to, say, the content of MC311. For MC312, we have these last two that are, for the most part, what we will be focused on. Ideal gases, whether it's variable specific heats or constant specific heat. And if you have constant specific heat, say cold air standard assumptions, we'll get to that later in this class, cold air standard assumptions result in a constant specific heat assumption. And you can get those specific heat values from table 7. So remember, constant specific heat might be written as our specific heat at constant pressure or specific heat at constant volume. Those are the two specific heats that we would be interested in. Okay, quick crash course on what we just saw in previous class. Let's review what we see for a closed system to help give us some guidance as we start talking about an open system. So for a closed system, we have exergy, we would say EX, at state I. So state I might be, let's imagine that we have a cylinder. This is a closed system, recall. We have a piston cylinder assembly, and we have some temperature and pressure inside of here. So Ti, Pi. So at some initial state, we have some exergy within that volume. And that's what we're talking about when I talk about a closed system at state I. So we have exergy at state I is going to be equal to our internal energy, big U's, times or plus this term, which is our dead state pressure and the initial volume minus the dead state volume minus our term associated with entropy plus dot dot dot, kind of running out of room there, plus terms associated with the kinetic energy of the system and the gravitational potential energy of the system. So this is equation 12.17. So one thing I need to note is on the outside of this system, so let's maybe draw this in blue, outside of the system we have a temperature and pressure. So say P naught and T naught. Those are what we describe as our dead state conditions. So a system is only going to be able to expand as low as the lowest pressure outside of the system. So imagine a piston cylinder assembly expanding to a lower pressure to say atmospheric pressure. So 1 atmospheric or 14.7 psi would be an example of P naught. So then let's think about exergy change. Let's think about exergy change. Well, I'm all over the place in terms of my writing. Exergy change during a process. During process 1 to 2. And this could be an example of, say, expanding from one state to another as that piston cylinder assembly rises. So we would have this equation where now instead of relating it to the dead state, we're relating it to from state 2 to state 1. And I point you to the text for the additional algebra that allows you to see that the dead state terms get canceled and they disappear. And when I say the dead state term, I mean notice how this is VI minus V naught and this is V2 minus V1. But we do still have P naught up here and we still have P naught right there because the system is always expanding against the surrounding atmospheric pressure for the sake of this example. So we still have to account for our kinetic energy terms. Now, I say that, but I do want to give you a hint towards the future, which is that for most conditions that we would be studying in this class for MC312, and we will often be saying that kinetic energy is negligible. So those V2 terms, or V squared terms, will often end up canceling out. Now that will be true for most of the beginning of the class, but actually as we begin to get into gas turbine engines, we will need to account for that velocity. Okay, so that's a quick crash course on closed system exergy to make sure that kind of refresh things. A couple things I want to point out. First of which, or actually one primary thing I want to point out, is the use of internal energy. Okay, we have internal energy in both of these equations, our big U's. And those are extensive properties, big U's, because they're still dependent upon mass. If we wrote them as intensive properties or independent of mass, we would write small U's. And we would write those as, say, specific internal energy. Specific internal energy would be little u. Okay, couple reminders there. All right, so looking for the next idea that we need to quickly review. That idea is the exergy balance. So we have an exergy balance that we need to account for. to understand how to analyze these systems. Now, unlike an energy balance, we have to account for that term that I talked about earlier, which is Exergy destruction. So if we say we have a change from one state to the next, state 1 to state 2, we could have Exergy transfer based upon heat, or we could have Exergy change based upon work, and then last, we could have Exergy due to destruction of Exergy that we need to account for in this balance. Notice that this term is negative, but remember our hip to win convention, hip to win, work in is negative. So if you put work into something, that negative is actually going to turn into a positive. However, this term, Exergy destruction, is always a positive term. So that minus term does actually mean that we are reducing the available work that is possible as a result of that Exergy destruction. So this is equation 12.26 to help give you, sort of some GPS to figure out where these things are in the textbook. Okay, so our Exergy, as it relates to heat transfer, we have this integral term, 1 minus T naught being the surrounding, and T boundary, right? So let's talk about T naught versus T boundary. T naught might be the absolute lowest temperature that something could decrease to, whereas T boundary might be the temperature immediately surrounding the engine. So you could imagine that around, say, a jet engine, there's an envelope of higher temperature air through which heat transfer is actually processing, whereas even further away from the engine is T naught. So an even lower dead state further away from the engine. So, and then we have this delta term associated with the amount of heat transfer that is actually happening. Okay, so then our work term, we have work 1, 2. So this might be, say, the amount of work that is happening as a result of that expanding piston assembly. But it has to be reduced, or the potential for it to do work is reduced as a result of expanding against P naught. Right? So in MC312, the work that you would often calculate for on a piston cylinder assembly was associated just with the amount of expansion that happened from that piston cylinder. But now you need to recognize that the actual amount of work that is going to be done as that piston is expanding against the surrounding atmospheric pressure, it's not going to be as much as you might have calculated in MC311. So we're trying to up your game here, give you tools to analyze real-world systems. And then last, Exergy destruction. So T naught, as we mentioned earlier, is related, or T naught times S production, entropy production. So this is, again, kind of an equivalent statement of the second law of thermodynamics. Okay, again, quick crash course on some of this stuff. Let's jump to the next topic, control volume. So we talked about closed systems. Now we're talking about a control volume. This could also be described as an open system rather than a closed system. This is an open system. And in this case, we could have mass transferring across the control surface being denoted as this dotted line here. Okay, so some good examples of control volumes or open systems, just like this turbine that we talked about right here. A couple others would be, say, compressor and pump. These are listed out in chapter 12. So say figures 12.6 and figure 12.5. Notice that we say adiabatic compressors and adiabatic pumps. Adiabatic. To actually define these things as being better adiabatic, or to visually display it, the text should actually have these little hash marks on here to note an insulated device. So that really means that it's adiabatic. So that's fair game. If that's on a WPR and we draw these dash marks around a device, you should recognize that it is adiabatic. Pro tip. Okay, heat exchangers and mixing chambers. In many ways, these are the same idea in terms of, say, transferring heat from one to the next. But of course, a mixing chamber could also get into, say, chemical reactions and such, which are beyond the scope of what we're going to talk about in this class. But nevertheless, from a heat transfer standpoint, both of these things are fair game as open systems, or what we call as control volumes. Okay, a quick commentary to close out video 1. Let's talk about flow exergy. So flow exergy for a control volume. This is the exergy associated with a flowing mass. So as I denoted or showed you with that turbine, say you have mass that's flowing into the turbine, and this incorporates flow work. Incorporates flow work. Man, I hope that rings a bell. What in the world is flow work? Okay, well, let's recall. Okay, so recall something about flow work. That something about flow work is how we define enthalpy. Enthalpy is defined as internal energy plus our pressure times our specific volume. And this term here, this is flow work. It is the energy associated with a flowing body of mass as it moves into a system, or at least the ability to do work as a result of that flowing body of mass. When it has a certain pressure and basically a specific volume, which remember is inverse of density. So it gives you an idea that basically you have a mass flowing into a certain system with a certain pressure, and that has an ability to do work. And that's how we define enthalpy. So when we talk about a control volume or an open system, we need to think about enthalpy, H. When we talk about a closed system, we use internal energy, U. Okay, so if we think now about this flow exergy on a per unit mass basis. So per unit mass flow basis. We could say exergy flow at a given point or a given condition would be our enthalpy of that fluid flowing in minus the dead state enthalpy, okay? Minus T naught, again, our dead state temperature, minus the difference in our entropies, plus a kinetic energy term, plus a potential energy term. Notice that I'm using a small ex, so we're talking about a specific property. So specific, I use that statement very precisely. Kilojoules per kilogram, that's what I mean. It has, say, energy per unit mass, which makes it a specific property. So then we have BTU per pound mass, would be in our English units. And this here is equation 12.43. And we're going to put a big red cloud around it. Why am I putting a red cloud around it? Well, because it's important. So it's important. So let's put a red cloud around it. Okay, if we said this on a rate basis, if we did this on a rate basis, we could have exergy flow, and I put a little dot up here. I hope you remember that from your nomenclature from MC311. And now we are multiplying our specific property, flow exergy or specific flow exergy, times m dot. So that results in a term or units of, say, kilowatts. Kilowatts being a unit of power, or BTUs per hour. I will say another little recall here. Recall that power is defined as energy divided by time. Okay, so then we have units of power, say like kilowatts. Okay, so this statement down here, This is the rate of exergy transferred across a control surface. Across a control surface with the conveyance of mass. Okay? As mass flows across these control surfaces, we can actually transfer exergy. Okay, so that wraps this up. I want to remind you why I'm showing this here to you at the end. Remember, this is for a control volume. We're talking about a control volume on this page. But notice how equation, let's see here. Notice how equation 12.43 is focused on enthalpy, H's. And if you scroll with me here, I'm going to scroll back up to have you see or remember or remind that when we were talking about a closed system, we were dealing with internal energies, U's. All right, so that's going to wrap this up. Next video on this topic is going to dive deeper into analysis of a control volume using exergy.